Here we have a few examples of bodies. Let's see where the instantaneous center of rotation of each of these links are. So the first example I have is a wheel that is rolling on the ground without slipping. So this is one of the cases you can reason where the instantaneous center is. Rolling without slipping means, by definition, that the point of contact have the same velocities. Otherwise, if the velocities of this red point on the wheel and on the ground would be different, then you would have a slipping. So by deduction, you can say when you have no slipping, this is your wheel instantaneous center of rotation or instantaneous center of zero velocity, because by definition of no slipping, that point has zero velocity. And you can make some deduction. For instance, if this is the instantaneous center, you have omega, velocity of any point is perpendicular to that. Similarly, velocity of this point is perpendicular to that one and proportional to the distance and so on. Okay, so that is one of the classical cases of instantaneous center of rotation. The other one is, the other example I have is when we have a wheel, but the wheel slips. Now the velocity of the center of wheel is potentially bigger than it used to be in no slip condition. And in this case, we know the velocity of the contact point is no longer zero because we have a slipping, but how do we find where that instantaneous center of rotation is? One thing I can note is that because I know velocity of the center, I know the instantaneous center must be somewhere along this perpendicular line, because the velocity of any point has to be perpendicular to the line connecting the IC to that point. So I know it is somewhere along here, but where along the line, I actually do not know. But I can calculate how far I am from that known point by knowing that my speed at the center must be this omega times the distance. So I can from here calculate d to be v over omega. So I can calculate it, and let's pretend it turns out to be here. And from here, actually, you can make further deductions. Any velocity of any point is proportional to the distance from there. So for instance, if you want to find velocity of the contact point where the slipping occurs, you can write or draw these proportional triangles to find velocity of slipping. So this is v slip. Okay, I have a few other example just as practice. I have on the left a slider crank mechanism. Let's find instantaneous center of each body. The first body is rotating about its base. So let's call this body 1, body 2, body 3. So this one is IC of body 1, because by definition that is a fixed point. That is what a joint is. What about body 2? We have to make some reasoning. So I know body 1 is rotating about that center, so it goes around an arc like this. So its velocity, I don't know which direction it is turning, but its velocity, I know it has to be tangent to the path So its velocity is along that line. Is it along that line? Kind of. Let's pretend that is tangent to the path. And from there, I know my instantaneous center has to be perpendicular to this direction of velocity. So it has to be along this line. So IC of body 2 must be somewhere along this line. We need another piece of information. The other piece, I can note that the other hinge point of body 2 is attached to body 3. That body 3 goes just back and forth. So the velocity of this point, I don't know which direction, but I know it is along that line. And again, the instantaneous center of body 2 has to be perpendicular to that line. So this is where they intersect, and that is where at this instant body 2 appears to be rotating. And finally, let's look at body 3. We know it is undergoing pure translation. So any point on the body goes along the same path. So all of these perpendicular lines to those velocities are parallel. In other words, IC of 3 is somewhere at infinity. So it is rotating about a point that is infinitely far. And because it's infinitely far, we really don't see the rotation. We only see the translation of it. Kind of, you can think of it that way. All right, so a few other points. I have in the middle a 4-bar mechanism. Again, these two hinge joints are the instantaneous centers of the two side bars because they are rotating about these fixed joints or fixed locations. So really the point of interest is the middle bar. I can do the same reasoning. Points go along arcs, meaning that their velocities are either along any of these two paths. So the instantaneous center must be perpendicular to these. Oops, this one isn't perpendicular. This is perpendicular. And where they intersect is the instantaneous center of your coupler link, the patterned ones. And at this instant, that triangle is rotating about that particular point. And you can, in a cascading way, often you can find instantaneous centers of other parts of a linkage. On the right, I have a 6-bar mechanism, which is the same one extended by 2 additional links. So we saw the IC of this one is roughly here. And from there, I know this third tip of the triangle has to have a velocity that is perpendicular to that direction. So the velocity of that point is along this line. I also know this one turns about that hinge point. So the velocity is along the tangent. Normal to these, well, kind of these are parallel. My drawing isn't great. Let me fix this. Turned out to be parallel. Let me fix it quickly. So let's pretend my other link is where is a good place? This is my other link. Why that side? This is my other link. Okay, now with this new configuration, this one still turns around that. This is the potential direction of the velocity, and normal to that is along this, and normal to the other point is along that. So this is the IC, instantaneous center, of this fifth link, this one. Let me color code. And color code this one, red. So by knowing the direction of the velocities and potentially knowing either the angular velocity or some other piece of information, you should be able to find the instantaneous center with relative ease. And in any problem that you deal with, if it's a rigid body kinematic problem, maybe always a good idea is to start by thinking instantaneous center, where that is, and that will simplify the problem quite a lot. So I stop here, and yeah, I'll see you later in another video.